We'll continue with the topic of convergence of random variables or of sequences of random variables. So now we discuss another notion of convergence, which is convergence in probability. We have a sequence of random variables, and they converge to a random variable x in probability. And again, don't forget from previous time that x may be degenerate, may be a constant random variable, maybe constant ones, surely. And we denote this as x. Now we write p to x, and you know, there are like two versions. They are equivalent, and so we take basically x minus xn. So that's like sort of the distance between you know, xn and x, and then we say that the probability that this distance exceeds any positive epsilon, okay, as n goes to infinity, this the probability of this event of the distance exceeding epsilon should go to 0. Or alternatively, we will say that in the limit as n goes to infinity, the probability that the distance between x and xn gets smaller than any arbitrary positive number epsilon, this probability should be 1. Okay? So again, this is like sort of a plausible definition. Convergence to a limit means that the distance gets smaller. Okay, the idea here is that we do not have a deterministic sequence, and so we take x, we take xn, and then we measure. You know, these are basically real numbers, and so we have a minus and then absolute value. So that's a distance. The idea now is that we need to adapt the conventional convergence results to the probabilistic setting in which these guys are basically now random variables. And so in convergence in the Rth mean, the idea was that to take the expectation of this thing raised to the power r, where r is greater than or equal to 1, and then investigate basically what happens for large n. Now we have another option, which is again plausible, which is to say, okay, so what is the probability that this thing exceeds any arbitrary positive number? So if we want convergence, we want basically the distance to be crushed to 0. So we want the probability that the distance is greater than any arbitrary positive number epsilon, that this should be 0 as n goes to infinity. Or alternatively, that the distance being less than epsilon, this should be 1 as n goes to infinity. Okay, so it's another definition for convergence that has its uses, right? So you know, some of you already know, you know, what is the meaning of a consistent estimator. So a consistent estimator is the notion of consistency is defined in terms of convergence in probability. So we have an estimator, and it is a sequence because, you know, it depends on the number of observations or measurements. And so if you have an estimator of, so basically xn can be the estimate for x using n samples. Okay, and so we say that an estimator is consistent is if basically if we have this convergence result in probability, then we say that xn is a consistent estimator. Okay, so the concept of consistency again is like, you know, is defined in terms of convergence in probability. Okay, you know, so the different notions of convergence, and we are still not done yet, are they related? So yes, they are related. I mean, so apparently the definitions are different, but of course, you know, we have probabilities, we have expectations, there are relations between them, and we can basically establish some results relating some notion of convergence to some other notion. So suppose that xn converges to x in the Rth mean, which means that basically this limit here is equal to 0. Now take this quantity for a positive epsilon, the probability that the distance between x and xn is greater than some positive epsilon. Now both sides here are positive, so you can, it's, you know, this probability is equal to the probability, you know, of the inequality with both sides raised to any power, I would choose power r such that r is greater than or equal to 1. And then this is a non-negative random variable, and so we can apply Markov inequality, and so this will be upper bounded by the expectation of this guy divided by epsilon to the r. Now, this is given, so if xn converges to x in the rth mean, this means that this expectation goes to 0 as n goes to infinity, so the upper bound on this probability goes to 0 as n goes to infinity. And since probabilities are non-negative, then it means that basically the limit as n goes to infinity of this probability is equal to 0, and that's exactly the definition of convergence in probability. So now we have a very nice result, that actually if you have convergence in the rth mean, you are guaranteed to have convergence in probability. Convergence in rth mean implies convergence in probability. The converse is not necessarily true. Okay, so you can come up with counterexamples showing that you have convergence in probability, but you don't have a corresponding convergence in the rth mean. Okay, so let's take an example. Xn is equal to n. Okay, so this is our sequence with probability 1 over n, 0 with probability 1 minus 1 over. So basically, xn is a two-valued random variable. It's either equal to 0 or n with probability 1 over n. Now let's check like convergence in mean square. So that's the special case when small r is equal to 2, and let's check convergence to 0. You know, again, 0 here like seems to be the thing to check, because like the probability of being equal to 0 like is increasing as n gets higher and higher. So do we have convergence to 0? Okay, you know, you do the test, you take xn minus the candidate limit, which is 0, square, you know, take the magnitude squared, and then take the expectation. Okay, so this will be n squared multiplied by the probability, which is 1 over n, that's n. And rather than going to 0 as n goes to infinity, this thing goes to infinity, so we don't have convergence to 0 in mean square. We don't have convergence to 0 in mean square. But let's try to check the definition of convergence in probability. Now, what is the probability that the magnitude of xn minus, again, the candidate limit 0 is greater than epsilon? Well, xn is a two-valued random variable. So basically, it's either 0 or the positive number n. And so, you know, the probability basically is, you know, greater than some arbitrary positive number, typically a small positive number, is the probability that xn is equal to n. And don't forget that by the end of the day, we are studying the limit as n goes to infinity. So n is becoming arbitrarily large. And so the probability that xn is greater than a positive epsilon is the probability that xn is equal to n, and from the definition here it's 1 over n, and that goes to 0 as n goes to infinity for every positive epsilon. So xn indeed converges to 0 in probability. So here we have an example in which you have convergence in probability. So the definition of convergence in probability is applicable while we don't have convergence in the rth mean. But basically using the Markov inequality, if you have convergence in the rth mean, and as a special case in mean square, that's it. I mean, you are guaranteed to have convergence in probability. So this is a counterexample telling you that you may not have basically the converse. However, in the homework, okay, so on homework 8, you will prove a partial converse. Okay, which means that, basically a sequence. So if xn is eventually bounded, okay, and you will see the definition in the homework, and xn converges in probability to x, then xn, I think the homework will be at least for the mean square case. Okay, so you can come up with situations in which you have convergence in probability and you are sure that you have convergence in let's say mean square. Okay, and so here one condition is that the sequence is eventually bounded, which means that the random variables, there is an index big M, such that for every small n greater than big M, okay, so there exists some big M, and there exists some threshold value, let's call it x0, such that for every n greater than big M, the probability that magnitude xn is greater than or equal to x0 is 1. Okay, so basically, the random variable is between minus x0 and x0 with probability 1. So it is eventually bounded. So if that's the case, then you are guaranteed to have convergence in mean square. This will be the problem. Okay, so but generally here is a counterexample. Generally no. Generally, so you need to establish it alone. There is a uniqueness theorem, which is like this is the place to state it. We have convergence in probability to 0. We examined convergence. We examined convergence in mean square to 0, and there was no convergence in mean square in this example. So you may think that perhaps there is convergence in mean square to some other limit. Okay, perhaps there is convergence in mean square to some other limit other than 0. So is it true? So the answer is no. Well, I mean, you can check convergence in mean square without even considering a limit by using the things we discussed in the previous lecture, like Cauchy criterion, okay, or or love criterion. Okay, so there are basically, and by the way, there are versions for this criterion for other types of convergence. Perhaps we'll see them in a homework problem or so. Okay, so yeah, I mean, you can do this. But there is another piece of information that actually tells you, rest assured that there is no convergence in mean square to any limit whatsoever. So it's uniqueness theorem, which tells you, suppose that you have convergence to a limit in some sense. So like here in our example, we have convergence in probability to the limit, which is big X is equal to 0. So here it just happens that the limit is a degenerate random variable. So the limit is X equals 0. So if you examine any other sense of convergence, mean square or arith mean, or almost surely, or distribution, or whatever, so in any other sense of convergence, you have two cases. Either you don't have convergence, or if you have convergence in some other sense, it must be to the exact same limit. So again, we are sure now that we have convergence in probability to 0. Now change this P to something else. Study convergence in some other sense. There are only two possible results. No convergence in this other, so no convergence in mean square, for example. But for example, if you study convergence in distribution, you will have convergence in distribution, okay? And if there is convergence in some other sense, it must be to the exact same limit. So it cannot be that xn converges in probability to 0, but it converges in distribution to 7. It must converge to the exact same limit random variable. Okay, so that's very, I will not mention here the proof. The proof is, a bit long, and it's a nice result, about uniqueness of limits here. Okay, and useful also because like now. Suppose that you do this step first, and then now if you study convergence in mean square, now you can justify why focus on 0 as a candidate limit. Okay, so it is justified because you have convergence in probability. So if you have convergence in mean square, it must be to 0. Otherwise, there is no convergence in mean square. Okay, so it is useful to keep this idea in mind. Third notion of convergence is convergence in distribution. Okay, and this is something that typically you are familiar with because the central limit theorem is an example of convergence in distribution. So again, a sequence of random variables converge in distribution here. Typically in this course I use big D, but some references use small d, not a big issue. And the official definition of convergence in distribution is the following. So it is a statement related to the CDF. Okay, so in convergence in the arith mean, we are using sort of an expectation. In convergence in probability, we are using a probability. Convergence in distribution, we are specifically making a statement regarding the CDF. And CDF, again, it's a reasonable choice because all random variables they have a CDF. right? So PDF is just for absolutely continuous random variables, PMFs for discrete, but we have mixed random variables and so on, and so CDF is like sort of a good choice. Specifically, we say that so we have this convergence if so this is the CDF. So this is the CDF of x of n. Okay, x, so if you put n equals 1, then this is the CDF of x1, CDF of x2. It must happen that as n gets very, very, very large, that this, this limit at a specific small x is equal to, is equal to the CDF of big X, the limit random variable evaluated at small x. There is a technical subtlety here. We care only about the values of small x at which this CDF is continuous. Okay, so this for every x at which. So it's not for every x in R. It's for every x at which f x of x is continuous. Okay, so that's the official definition of convergence in distribution. Okay, what if you are talking about small x at which basically this is not continuous? We don't care. And we know, I mean, like, basically, if x is a discrete random variable, if big X is a discrete random variable, then basically it has, it has points of discontinuity. And so, basically, the CDF, I mean, the CDF, it's, it may have, for discrete random variables, for mixed discrete and absolutely continuous random variables, you will have, like, basically those jumps, and at those jumps, we don't care. But we say that there is convergence in distribution. A convergence in distribution, you need basically this limit statement to be true at values of small x at which the CDF of the limit random variable is continuous. Central limit theorem or central limit theorems, because there are several versions of them. So for example, the typical version. So like if I just say central limit theorem, then the version, the thing that will come to your mind is basically the IID case, in which basically you have those guys are zero mean, they have a finite variance, and this quantity here. Okay, this quantity. So what is our sequence of random variables? What is the sequence of random variables? Okay, so the sequence is, if you take small n equals 1, so it is x1 over square root 1 sigma. And then what is the second guy in the sequence? So the sequence that we are studying here is x1 over square root 1 sigma, and then x1 plus x2 over square root 2 sigma, or x1 plus x2 plus x3 over square root 3 sigma, and then x1 plus x2 plus x3 plus x4 over square root 4 sigma. So basically, we are studying not the sequence x, we are studying this sequence, let's say y, okay, y3, y4. So we have convergence to basically the standard Gaussian, you need the x's to be IID, and you need basically the second moment to be finite. Okay, so you need the second moment to be finite. There is basically a Lippanov central limit theorem, which also requires the random variables to be independent, but they do not need to be identically distributed. Okay, so perhaps you have seen it, or again, like you may see it in some exercise. Okay, convergence in probability. Officially, you do it with the CDF, but like if you want to prove the central limit theorem, you are stuck with something that is very difficult, which is like we typically, the sequence of random variables, like they have an increasing number of terms like this, and suppose even that those guys are absolutely continuous random variables and they have PDFs. So how can you what is the PDF of the sum of two independent random variables? What is the PDF of the sum of 3 or 4, or I mean, we are taking the limit as n goes to infinity. So PDF, we convolve, right? We have convolution. That's painful. This is very, very painful, right? So to study basically the CDF of a sum of random variables, a sum with an increasing number of terms is, perhaps it's actually infeasible, like to basically make your study based on the CDF. Now, if you are taking the maximum, well, the maximum of independent random variables, perhaps it's easy to study using the CDF. but something like the sum is like horrible. Okay, and so you know, you have to do convolution, repeated convolutions. Does not make any sense actually to use the CDF. So here's the good news. Rather than using the CDF, we can use the characteristic function. So for every random variable, for every type of random variable, we have the characteristic function. So so there is again a theorem that is very nice called revised continuity theorem. Okay, and like if we its proof may take like 2 lectures or something, so we'll just take it for granted. Very nice. You know, the moral of the story is, you know, you can study, you know, the convergence of the characteristic functions. Okay, so basically you study the convergence of the characteristic functions. Okay, so you study this thing here, and if this converges, so if converges to phi of u, you need only something that, you know, the limit, you know, to phi of u, which is continuous at 0, which is continuous at u equals 0. Then we have convergence in in distribution. Then we have convergence in distribution. Okay, and so like if you want to prove the central limit theorem, the way to go is characteristic function. Okay, you know, of course, I mean, the question is, so you know, what is nice about the characteristic function? Well, I mean, so many nice things. One of them is that basically phi of x1 plus x2 plus x3 and so on plus xn. So if those guys are independent, then the characteristic function of the sum is basically the product of the characteristic functions. Okay. That makes things much easier, right? So it's like the Fourier transform. Okay, so it's like the Fourier transform. You, rather than having convolution, you are basically having a product, and much easier to handle. And then thanks to Levi's continuity theorem, well, we are justified. I mean, you may say, well, but we are studying the characteristic functions, not, you know, the definition is saying that we should study the CDFs. Well, it's not an issue. Okay, so basically we are resting on this very useful theorem, because again, in many cases, the way to go when you study convergence in distribution is to use the characteristic function and not the CDF. The CDF will not make any sense. Okay, in terms of, you will not even be able like to write down anything meaningful with it. Okay, any question? Okay, so that's it, like the third type of convergence now. So we have convergence in the arc mean, convergence in probability, convergence in distribution. So what is the relationship between convergence in distribution and convergence in probability, the previous guy? So you know, the conclusion will be convergence in probability implies convergence in distribution. So if you have convergence in probability, you are guaranteed to have convergence in distribution. Okay, so let's prove this really quick. That's the CDF of x of n, and of course you pick an epsilon that is greater than 0, and then so the CDF is the probability that xn is less than or equal to x. And so you basically use the law of total probability, and you say that the probability of this event, then you add basically 2 here events, x, so that's the candidate limit or the limit, x less than or equal to small x plus epsilon, and x greater than x plus epsilon. Okay, and what we will try to do is basically to upper bound. Now for this term, the probability of A intersect B is basically, so an upper bound will be basically this second guy here. Okay, what about this term here? Then well, we have 2 events, right? So we have 2 events. One of them is big X greater than small x plus epsilon, and the other one, after multiplying by a minus, will be minus xn greater than or equal to minus x. So if these 2 events are true, then this implies the following. You can just add the inequalities, and the inequalities will tell you that x minus xn is greater than x plus epsilon minus x, which is epsilon. So x minus xn is greater than epsilon. Now, if x minus xn is greater than epsilon, okay, then absolute x minus xn is greater than epsilon. Okay, so basically these 2 events together, they imply basically this. Okay, so we know this rule that, you know, if, you know, A implies B, then the probability of B is greater than or equal to the probability of A, because like this implication means that whenever A is true, B is true. B is guaranteed to be true, but B can be true also for other reasons. Okay, so so this is actually the implication. It means that whenever A is true, then B must be true, but B actually can be true also for other reasons. So it can be false and still B is true. So so the probability of event, so it's like if you use like set theoretic expression, so it's like event A. So by the end of the day, the official definition of events that they are subsets of the sample space. So it's like A is a subset of B. Okay, so that's basically one of the properties of probability measures. If A is contained in B, then probability of A is less than or equal to the probability of B. Okay, so very useful. So so basically these two guys together, they imply this event. So this event has a probability that is an upper bound on this probability here, and so so this guy is upper bounded by eliminating one of the guys, right? Probability of A intersection B is less than or equal to the probability of, let's say, A, and here we did this trick, and so we have these two terms here, and this first term is the CDF of big X evaluated at small x plus epsilon. Okay, so that's one inequality. So we do something similar, but like we start now from the CDF of x minus epsilon, and we do similar steps, and we reach another inequality. Okay, and the two inequalities can be combined like this inequality here, and this delta n is the probability that xn minus x is greater than epsilon. Okay. So again, what is our objective? What is given, and what is basically what is required to prove? So what is given is that we have convergence in probability, and we want to show that convergence in probability guarantees that there is convergence in distribution. So convergence in probability means what? So this delta n here, basically this is exactly, this is the quantity that if you want to study convergence in probability, you will take its limit as n goes to infinity, and the limit should be equal to 0. Okay, so we know because xn converges to xn probability, then limit as n goes to infinity of delta n is equal to 0. And because the limit exists, okay, but by definition, because we take it as our starting point is that we have convergence in probability, then also lim inf of n tends to infinity, delta n is 0, and lim sup as n goes to infinity of delta n is equal to 0. Okay, so the objective now is to show that that in this case we indeed have convergence in distribution. Okay, and so here is the way to go. Basically, take these two guys. So this inequality, I mean, take lim inf. Okay, so lim inf, basically we have lim inf of this sequence. Lim inf because we don't know even whether this sequence converges or not. We have no idea. Okay, let's discover. And the left-hand side, so the left-hand side, two terms. This term is not depending on n, so there is no n here anywhere. And this guy, lim inf will be 0 because of we have convergence in probability. Okay, so now basically study this inequality here, but now take lim sup. Again, you will leave lim sup here as is. Okay, so lim sup, I mean, we don't know lim sup, but for the other side. Again, this does not depend on n, and this will go to 0 as n goes to infinity. Now we know from the previous lecture, or from previous study of analysis, that lim inf is always less than or equal to lim sup. Okay, so so we can basically combine these inequalities by like taking this. Okay, so let's do it. So what we'll do is that we will take this two guys with these two guys like this. Okay, knowing that it's always the case that lim inf is less than or equal to lim sup. Okay, and now we have something like this. It's different from the previous lecture. In the previous lecture, we had like the quantity on the very left and on the very right was the exact same quantity when we did the proof of like the convergence of the sequence of moments in Arth mean, when we have convergence in the Arth mean. Now we have two guys that are they are different, right? So here we have, the CDF of big X evaluated at small x minus epsilon, but here it's a small x plus epsilon, okay? Okay, so, but what if we take limit as epsilon goes down to 0. Well, okay, you can do so, and if the CDF of big X is continuous at small x, then actually when you do the limit as epsilon goes to 0, then these two guys will be equal. So they will be equal only, they are guaranteed to be equal only when you know that the function is continuous, like, because like, if you take this limit as epsilon goes to 0, so one, it's like you're taking the limit of the CDF from the left and from the right. Well, if you have a jump, these two guys will not be the same, and you cannot conclude that these two guys are the same. However, if a small x is a point of continuity of the CDF of big X, then, if you take the limit as epsilon goes to 0, then these two guys will coincide. And in that case, you can, as in the previous lecture, say, oh, okay, so lim inf is equal to lim sub. So the limit exists, and the limit will be equal to fx of small x. Okay. Now, do we have any trouble? No, because the convergence in distribution basically requires that you have the limit statement satisfied at values small x at which the CDF of big X is continuous. Okay, so so this is actually the case of interest. If at small x the CDF of big X is not continuous, we don't care about what's going on. Okay, so and perhaps actually the definition of convergence in distribution is written in this way, so that we get this result here, that convergence in probability implies convergence in distribution. Okay, so that's again a nice result. So now we know that convergence in the Rth mean. So this thing implies convergence in probability. So here the proof is a one line using Markov inequality, and now using this slide here, we know that this implies convergence in distribution. Okay, the converse here is not necessarily true, but it can be true under some cases. What about this converse? So if you have convergence in distribution, do you have convergence in probability? Okay, so let's see this case. Any questions? So I think in the notes you'll find like a counterexample. So you can find convergence in distribution and no convergence in probability. However, if you have convergence in distribution to a degenerate random variable, to a constant, then you have also convergence in probability. So convergence in distribution to a constant implies convergence in. So there is also a partial converse. Okay, and here is the proof. It's not difficult. You can go through it. Okay, and this is like a very useful result, because so it allows you to study also convergence in probability. I mean, like if you gather what we have been saying, so how to study convergence in probability. So now, if you follow basically this lecture, you'll find that actually there are several options. One, show convergence in Rth mean. Okay, and this automatically will imply convergence in probability. Or show convergence in distribution to a constant. Right? Or what? Use the definition. Use the main definition of convergence in probability. Okay, and it will come later that show convergence almost truly. Convergence almost truly. Okay. The idea is that sometimes those are like equally challenging or equally easy or something, but sometimes one of them like is easy and the others are tough. So you have options. Like, so if you exploit the network of relations between the different notions of convergence, but because like perhaps basically showing convergence in distribution to a constant is like sort of easy in some situation, and you just go for it, and automatically you will get convergence in probability, because we have this we have this theorem that convergence in distribution to a constant implies convergence in probability. So let's now prove very quick basically the weak law of large numbers. So the weak law of large numbers tells you that that if you have an IID sequence of random variables with a finite first moment, so finite first moment, then if you sum the random variables and divide by their sum, okay, then you have convergence in probability to the to eta is basically the first moment. You have convergence in probability to the first moment. Okay, so this is actually the motivation. Like in many things, when we estimate a certain quantity, we do this. Like we collect observations and then we take the average, right? We sum them. We sum the observations and then we divide by their number. So the theoretical foundation of this widely used idea is basically this, the law of large numbers. And it is called the weak law of large numbers because we have, this statement is about convergence in probability. We can actually show that the convergence, convergence happens also almost surely, as we will study. Okay, so weak. Why it's called weak? It's because we are using here convergence in probability. There is a stronger notion of convergence that is also valid, and its proof is like more involved than the proof here. So the proof here will be, okay. So how can you show this? Okay. So try to do it from the definition of the convergence in the direct definition of convergence in probability. Okay, so it's a nice exercise today. Like you take this thing minus eta and show that the probability that this greater than epsilon is 0 as n goes to infinity. Now and then so it's a probability, and then you have this evil thing which is the summation. Okay, try it. Try even to show convergence in R3, again just using the assumption that the first moment is finite. So you'll find that it is not easy at all, but it is easy to actually to do convergence in distribution because actually if we use the characteristic function, the characteristic function of a sum is very easy. Okay, because again it's like a Fourier transform. You don't need like to do convolutions or anything. You just multiply. Okay, so suppose that Zn is basically this quantity here. It's the average of x1 plus x2 up to xn. What is the characteristic function? So the characteristic function is the characteristic function of the sum, and each one of those guys is scaled by 1 over n. Now, the characteristic function of the sum is the product, because the random variables are independent. So we have the product of characteristic functions. But here they are not just independent, they are also identically distributed. So the characteristic function is the characteristic function of one guy raised to the power n. And because of this scaling factor 1 over n, we have here u over n. Now let's study the logarithm of the characteristic function. Logarithm is a continuous function over r plus, so it's limit statements regarding the logarithm can be transferred directly to the characteristic function itself. So take the logarithm, and so you get this result here. Okay, so what we need to study is basically the limit of this thing as n goes to infinity. So what we can do is that we can replace n. You can replace n by 1 over alpha. Okay, 1 over alpha, and alpha is a continuous parameter, and then take the limit as alpha goes to 0. Right. So what we'll do is that we will rewrite this thing as 1 over alpha ln phi x of alpha u. Okay, and then we study the limit. Alpha goes to 0. If you put u equals 0, to have an understanding of what's going on, if you put u equals 0, the characteristic function evaluated at 0 is 1. We know this. Moment generating functions and characteristic functions at 0 give you 1. Len 1 is 0. Alpha at 0 is 0. So it's a 0 over 0 situation. Okay. So when we do the limit, it's we need to do something, perhaps like apply L'Hopital's rule once. Okay. Now L'Hopital's rule requires that you differentiate, and now we will have to differentiate the logarithm using the chain rule. So we'll have basically 1 over the characteristic function multiplied by the first derivative of the characteristic function with respect to alpha. But who says that the characteristic function is differentiable? Right. So if you go and review what are the properties of characteristic functions. So what is the property that is guaranteed for characteristic function? That is differentiable. What is the property that is guaranteed for characteristic functions? Hello? It is uniformly continuous. So characteristic functions are uniformly continuous. So uniform continuity is a stronger notion of continuity. You can show, and it's not that difficult, that they are uniformly continuous. Now, to go from continuity, or specifically from uniform continuity, and make a statement regarding differentiability, you need restrictions on the moments. Okay, so basically for the characteristic function, I mean, a sufficient condition that actually will, and I think it's also necessary, it's sufficient and necessary condition for the characteristic function to be differentiable once, is that the random variable has a finite first moment. So without that, you cannot apply L'Hopital, because again, when you apply L'Hopital in our context here, you will have to differentiate the characteristic function, and the question arises as to whether actually the characteristic function is differentiable. It's not one of the properties of the intrinsic properties of characteristic functions. They are uniformly continuous, but differentiability requires a finite first moment. And so now you understand why actually the theorem requires that you have a finite first moment, so that now you can do this step. Okay, and now because the random variables are, you have the first, this is the first derivative, and once you evaluate the first derivative at 0, you will get basically the first moment. So the first derivative of the characteristic function at 0 will give you like I multiplied by the first moment or something like this. Okay, so basically, so here what we show is that the limit as alpha tends to 0 of 1 over alpha len phi x of alpha u, that basically this will be iu expectation x. The u will come again because the chain rule, when you differentiate with respect to alpha is multiplied by u, so you will get a u. And again, the value of the characteristic function at 0, it will give you this I, and then the first moment, which here I called eta. Okay, and so it's true that limit is n by Heinz theorem, that limit n goes to infinity, and phi x of u over n, that this will also be the same limit, iu expectation x. And then you basically take you exponentiate both sides, then limit n goes to infinity of phi x of un raised to the power n. So that's basically the characteristic function of the sum divided by n. So it will go to e to the iu expected x. What is the random variable? Whose characteristic function is e to the iu multiplied by a constant? It's a random variable that is constant. Okay, so basically here we have, and note that this function also we are talking about is continuous at u equals 0. So Levi's continuity theorem is applicable here, right? So you study the convergence of the sequence of characteristic functions, and you will reach some function. Now, if your function, you need just to check one tiny thing, that the characteristic function, that the limit of the sequence of characteristic functions is something that is continuous at u equals 0. If you have continuity at u equals 0, you are done. Then you can say that you have convergence. You have convergence in distribution to the random variable whose characteristic function is this guy. And this is a random variable, that is equal to expected value of x almost surely with probability 1. And so that's a constant random variable. And so we have convergence in distribution. And because it is convergence in distribution to a constant, then it is also convergence in probability. Okay, so this is the proof of the weak law of large numbers, and we used here again like nice things, the characteristic function, and this result here again, its proof is not difficult at all. You can basically skim through it. Okay, are we done with convergence? Of course, no. I mean, we are left with one guy that's very important, appears a lot, which is, and whenever you see the word strong. So we need now to talk about almost sure convergence. So almost sure convergence, okay, or with probability 1. So it is written, it's up to you, depending on your mood. You can use it like this, or with probability 1, and it's like it involves a probability like convergence in probability, but the probability here is like a bit more complicated. Okay, so so in probability, like we have to put things. So in probability, convergence in probability, like you study that basically the limit of this thing, okay, is equal to 1, right? Now it is something else, right? Now we have the probability that the intersection, so we need like an intersection here, n from m up to infinity. Let's just put it like n greater than or equal to m, xn minus x less than epsilon. So here the probability of the event, okay, so let me continue it, and then I will go. Then limit m goes to infinity, that this should be 1. Okay, so what is this event here? What is this event? So this is xm minus x is less than epsilon, and xm plus 1 minus x is less than epsilon, and xm plus 2 minus x is less than epsilon, and xm plus 3 minus x is less than epsilon, up to infinity. Okay, so it's like a tough condition, right? So here we just have like this event, but here we have basically those those events must be true. And there is also a union version with greater than epsilon, and of course both are equivalent. Okay, so one way of understanding this, which I think is very nice, and it's sort of another application of the Borel-Cantelli lemma, is because you look at this probability and like it may seem mysterious, but actually let's try to express this probability in terms of like those infinitely often thing, the stuff that you have learned when you studied the Borel-Cantelli lemma. Okay, so we have something called continuity of probability, and you can use continuity of probability in our context here to show, for example, that this limit here is exactly equal to this probability. Okay, so limit m goes to infinity, then probability of intersection, and again you can sit down carefully, and proceed carefully, and you can use continuity of probability. Again, it's something like you have seen like during the derivation of the Borel-Cantelli lemma itself, that basically this probability is equal to that probability. So almost sure convergence or convergence with probability 1 is basically this statement. So there exists an m. Okay, so you can read it like this. So there is a union here, there is an intersection there, and then there is this event in which x, the distance between x and minus x, is less than any arbitrary positive number epsilon. Okay, so we can read it like this. There exists an m, right? Because you have a union, so it must happen that there is at least one value of small m. We don't care. It may be a huge number. Okay, a number that is, you cannot even fathom. You cannot even, it's even bigger than any number used in physics and anything else. But who cares? Okay, there exists some finite number, no matter how large, such that for every n greater than or m, basically this event for every n, it's not for just one n, for every n greater than or equal to m. So this is the thing that I wrote here: xm minus x and xm plus 1 minus x and xm plus 2 minus x, and so on, with absolute values that basically less than epsilon. This happens with probability 1. And we can say that that basically absolute value xn minus x is less than epsilon eventually. So there is some index and time. Beyond which, with probability 1, magnitude xn minus x is less than epsilon. Okay, we can also study this guy again. Same concept. We can apply the we can use continuity of probability and say that this limit with this intersection here is exactly equivalent to this. So what is this thing? How do we write it? Okay, so for every m, okay, it's not written here, so actually I can write it. So for every m, natural number m. Okay, so you choose m. The following statement is valid for every m. It must be valid for every m. For every m, there is a corresponding n. Okay, so there exists some n greater than or equal to m, such that xn minus x greater than epsilon. So that's the event. So this is the event. So it means that for every m, no matter how large, there is an n greater than or equal to m, such that at this n, the distance between xn and x goes above epsilon. It exceeds the threshold epsilon. Now, in deterministic convergence, if we see an event like this, it means what? No convergence, right? Again, see what this is saying. It says that no matter what m is, there is always an n greater than or equal to m, such that at this n, xn deviates from x by more than epsilon. The distance between the two guys exceeds epsilon. And this is true for every m. Then can we say that xn converges to x? No. So deterministically, that if these guys are deterministic, we will say that actually this is the exact definition of xn not converging to x as n goes to infinity. Now we have random variables. So basically we want the probability of this event, which is our friend from Borel-Cantelli lemma. So this is the probability that xn minus x greater than epsilon infinitely often. It always happens. It never stops occurring. We want this probability to be exactly 0, so that we talk about convergence. Okay, so almost sure convergence again. So you can understand it using this and that definition. You can apply the continuity of probability and understand it using this and using that. So it's a bit more sophisticated than convergence in probability. Okay, so it is a stronger notion, and it is the closest you can get to the definition of deterministic convergence. Okay. I mean, just by looking at the definitions, you feel like convergence in almost sure convergence is like a stronger notion. And if there is almost sure convergence, then you are guaranteed to get convergence in probability. And that is true. Okay, so the next few lines are basically telling this story. Okay, so take the probability of this event. So basically intersect n greater than or equal to m, distance between xn and x less than epsilon. So this, you have intersection here, right? So when you have intersection, then this probability is less than or equal to, you take any one of the guys, and you may even take the infimum. Okay, so we know this, probability. Once you intersect, I mean, so like if you think of it in terms of sets, right? So if you intersect, then basically you are getting something that remains as is or gets smaller and smaller and smaller. And so basically this probability is bounded by the infimum over n greater than or equal to m of this probability. Now take limit as m goes to infinity of both sides. Okay, so for the right hand side, if you take the limit as m goes to infinity, you will get the quantity that is in the definition of almost sure convergence. What about the left hand side? So for the left-hand side, if you take the limit as m goes to infinity of infimum n greater than or equal to m of this probability, that's actually the definition of limit infimum. So it means, so you have the limit infimum n goes to infinity of basically of this quantity. Okay. So now suppose that we have convergence with probability 1. We have almost sure convergence. So what does this mean? what does it mean that we have almost sure convergence? It means that this limit, by definition of almost sure convergence, this limit is equal to 1. So this limit is equal to 1. So now we have the limit infimum. Okay, so basically now we have this inequality that 1, because we have convergence almost surely, 1 is less than or equal to lim inf n tends to infinity of this probability xn minus x is less than epsilon, right? And lim inf is always less than or equal to the lim sup, right? And probabilities, you are telling me about probabilities, they are always upper bounded by 1, right? And so we have, the chain that we have been seeing, that basically, if we have almost true convergence, this guy here, so there was basically a limit here. Now it is 1 if we have almost true convergence, and so basically the limit infimum is equal to limit supremum, and so the limit exists and it is exactly equal to 1. And see, what limit do we have? Oh, it's the limit basically used in the definition of convergence in probability. Okay, so the idea is that almost sure convergence ensures convergence in probability. Okay, what about the converse? The converse is not necessarily true. The converse is not necessarily true. So you may have convergence in probability, and you don't have almost sure convergence. But almost sure convergence will automatically give you convergence in probability. Okay, so again, a nice result. And in the homework, in homework 8, you will prove that if you have convergence in probability of a sequence of random variables, then there is a subsequence that converges almost surely. Okay, so again, convergence in probability does not imply convergence almost surely, but you can extract the subsequence from the original sequence that converges almost surely, and this is used a lot in proofs. Okay, that you say, okay, I have convergence in probability. Well, I cannot say that my sequence converges almost surely, but I am sure that there is a subsequence that converges almost surely. Okay, so it's a classical result in probability theory that is again very useful in proofs. Okay, so again, you will show it in the homework. Okay. So, example, those guys, x's are IID Bernoulli 1/2, but actually we are not interested in the x's themselves, we are interested in yn, and so yn is this quantity, so you multiply the x's from 1 to n, and then you multiply by this monster here, 2 to the power n, and you ask yourself, does this thing converge to 0 almost surely? Does this thing converge to 0 almost surely? Okay, so it may look scary, but actually it is not, because like the x's are Bernoulli random variables, and so Bernoulli half. So basically they are either 0 or 1, and now yn is equal to a product. Okay, so if one of the x's is equal to 0, that's it. Yn will be equal to 0, and for yn to be equal to 2 to the power n, it must be the case that all x's are equal to 1. Okay, so basically yn is 2 to the power n with probability 2 to the minus n. This probability is exactly the probability that n IID Bernoulli half random variables, all of them are equal to 1, and otherwise basically 0, and so basically the probability of 0 is 1 minus 2 to the minus n. Okay, so now again, what is the probability that union n greater than or equal to m of yn minus 0? So basically this is the limit, the candidate limit now. What is the probability of this thing greater than f? So here I am checking almost true convergence by simply using the definition of it. Okay, so we want this limit to be basically 0, to go to 0, right? So if you have greater than epsilon here, then you want this event to have a probability that basically is 0 as m goes to infinity. So we want the probability. What is the probability that yn exceeds a positive number? Well, again, yn is a two-valued random variable. It is either 0 or a positive number 2 to the power n, and this, and by the end of the day, we're taking limits as n gets very large, or n gets very large, and n is greater than or equal to m. Then basically the probability that that you exceed epsilon is the probability that yn is equal to 2 to the n, is equal to 2 to the n here. Okay. Now, what is this probability? What is this probability? Okay, union. Okay, so that's an evil thing. Sometimes here it's useful to use the union bound. So sometimes it will work, sometimes it will not work. Okay, so so basically you are encouraged, by the way, that in the notes to like to study as soon as possible. Perhaps like use that the coming Sunday and Monday there are no lectures or anything. I mean, convergence problems can be very tricky, and you can have all sorts of things happening. It's not like there is like a fixed procedure for solving them. Okay, so sometimes you need like to try, and like you need to keep like many tricks in mind, and some of them may work in some contexts, may not work in other. So sometimes the union bound is the way to go. It is one thing that you should keep in mind, especially if you are doing like convergence in almost surely. So so here is a probability of a union. Okay, but you can say, well, it is by the union bound, it's less than or equal to the sum, and the probability that yn is equal to 2 to the n is 2 to the minus n. And the sum of 2 to the minus n from 1 to infinity converges. That's a converging geometric series. Then if you start the summation from m and then take the limit as n goes to infinity, this will go to 0, and so we have convergence. We have convergence almost surely. Okay, so we have. Okay, so the idea here, why is the union bound nice here? Because we were able to upper bound so we want, if there is almost true convergence, we wanted this thing to be equal to 0. If you want something to be equal, a probability to be equal to 0, this is equivalent to showing that it is less than or equal to 0, because probabilities are non-negative. So if it's less than or equal to 0, it is equal to 0. But if you upper bound it by something that is positive, then the upper bound is useless. It's like if you tell me that this probability is upper bounded by 0.1, I cannot make it. I want basically the definition of almost true convergence tells you that this thing must be 0, right? So you need to upper bound it. You need to upper bound it by something that is 0. Okay, so that's sometimes a challenge. Sometimes like you write down things, you apply the union bound. No, it's not giving me what what I need. So again, it's not it's not like universal trick, but it's useful in many problems to use the upper bound. A comment, something related to the previous lecture, which is, so here in this example, yn converges almost surely to 0. By the previous argument, actually it converges also in probability to 0. Okay, so actually let's write it, right? So we know this chain of implications. Very nice to keep in mind, because like suppose that I give you a problem, tell you study this sequence of random variables in terms of convergence using all notions of convergence. So suppose that you start with almost true convergence and you prove that this statement is true. Then you are guaranteed, you just write down this arrow. It implies that yn converges in probability to 0, which implies that yn converges in distribution to 0. Nothing is needed now. Okay, so we just use these implication results. So once you expend some effort in cracking whether the sequence converges almost surely or not, then if it does, then automatically you get a convergence in probability, which automatically entails convergence in distribution. But let's now talk about the moment. Okay, so what is the expected value of yn? Expected value of yn, so basically this thing here is 0 multiplied by 1 minus 2 to the minus n plus 2 to the n multiplied by 2 to the minus n. Okay, so you take each value multiplied by its probability and you sum, and this is 0 and this is 1. So the sequence y, so the sequence y1, y2, y3, y4, and so on. What is the mean value? What is the mean value of yn? The mean value of yn, so if we take the sequence, so the sequence of moments is a deterministic sequence. It is a deterministic sequence. Each element in that deterministic sequence, 1, 1, 1, 1. And so this sequence converges to what? To 1, despite the fact that the sequence of random variables converges almost surely to 0. It may sound like a counterintuitive result, but it's very important. I tried to say that, the previous lecture, it was not clear. Like, when I said that there is convergence in the Rth mean xn converges in Rth mean to x, then expectation of xn to the q, so that's the qth absolute moment, converges. So this is a deterministic sequence, converges to x q, and then q is greater than or equal to 1, less than or equal to r. This is not something that is, you may think that, it should be the case. I mean, it's the case for the rth moment, and note that it is not true for any moment. Q must be greater than or equal to 1, less than or equal to r. But for a strong, an equally strong notion of convergence, like convergence almost surely, it's completely not valid. I mean, so basically the first moment, the sequence of first moments it converges to 1, while the sequence of random variables, if you study based on the definition of almost true convergence, it converges to 0, to a degenerate random variable that is equal to 0, and so its first moment is 0, its second moment is 0, and so on and so forth. Right? So this is very important to keep in mind, that basically a convergence of a sequence of random variables, is, you cannot just take it and say, okay, so if I take the moment, some moment of each guy, then the sequence of moments will converge to the moment of the limit random variable. So this may be true, like in convergence and rth mean, for a particular values of q. It may be completely false for other notions of convergence, like convergence almost surely. Okay, and you can check here actually that there is no convergence in rth mean. Okay, so you'll find that actually that the limit, that if you study this quantity, the limit as n goes to infinity is not 0. So there is no convergence rth mean, which means that almost true convergence and convergence rth mean, basically you can find the 4 cases. There are examples for the 4 cases. So you can find convergence in the rth mean, and at the same time you have convergence almost surely. You can have convergence in the rth mean, no convergence almost surely. You can basically have no convergence in the rth means and convergence almost surely, and you cannot have both at the same time. So basically you can find examples for each of those 4 cases. Okay, so they are sort of living. So these 2 notions are sort of, if you want like to check them, like you need to do like separated checks. Okay, while convergence and probability, again, if you show convergence in the rth mean, or you show convergence almost surely, then automatically you get convergence in probability, and this implies convergence in distribution. Okay, but almost, in the rth mean and almost sure convergence are sort of like a bit different in nature. Okay, so they don't imply one another, generally speaking. Okay, so another example here. Basically, this is a sequence of independent random variables: 0 with probability 1 minus n, 1 with probability 1 over n. Are there, like, can we study the almost sure convergence to 0? I think at the beginning of the lecture we showed that there is convergence in probability to 0. For almost sure convergence, here we take this version. What is the probability that that xn for every n greater than or equal to n is less than epsilon, is less than a positive number, and xn is a two-valued random variable. So being less than an arbitrary positive number means that we study that xn is equal to 0, and this probability is 1 minus 1 over n. So this is the probability. Are we done? Of course, we need to study what is the limit as n goes to infinity of the probability that intersection n greater than or equal to m xn minus 0 less than epsilon. What is this thing? Is it 0? If it's 1, it must be 1. Then we have almost sure convergence. If it's anything other than 1, okay, so we need this thing. So the question is it 1? Okay, so in fact, in our case here, you can show that it is 0. Okay, so but if you get 0.1, it is the conclusion is the same. You don't have almost sure convergence. And here is basically why this limit. Okay, so the idea is simple, and again, a trick that is like sort of common. So you have something like this. Basically write down the infinite product using its definition. So infinite product means that you stop at some upper bound Okay, and then you take the limit of this upper bound getting very large, right? And so what is this quantity? Is n minus 1 over n. Then write the terms. So the terms would be m minus 1 over m. Okay, and then it's m over m plus 1. Then m plus 1 over m plus 2. All the way to, so the last term will be k minus 1 over k. And you'll discover that, okay, and so on. So it's like a telescopic product. And this telescopic product, again, you will end up with m minus 1 over k. And again, note that you do the infinite product first, and then you take the limit as n goes to infinity, right? So in other words, you do this limit first. So when you do this limit first, this thing will be crushed to 0. And so the limit will be equal to 0. So basically, so again, like in slow motion, it is limit m tends to infinity, limit k tends to infinity of m minus 1 over k. So this is limit m goes to infinity of 0. Okay, so 0. And so the limit of the O0 sequence is 0. It's constant. It converges to the same value, which is 0. And again, if you go to anything other than 1, then there is no almost sure convergence. Okay, so this is an example that there is you can have convergence in probability, but not almost true convergence. But the converse, of course, is if you have almost true convergence by the argument I said, like somewhere here, this one, then you are guaranteed to have a convergence in probability. Any questions? There is another definition that you will see in the literature regarding convergence almost surely, which is this, that you have almost true convergence. You will find, people write actually a deterministic limit inside the probability, which is basically to tell you that almost true convergence is like sort of, it's the notion of convergence that is by definition is the closest as you get to like the classical convergence of deterministic sequences. Okay, so probability that limit n tends to infinity x of n is equal to x is equal to 1, and it depends on what textbook you are studying from. Sometimes actually people start the topic of almost sure convergence by writing down actually this expression here. Okay, so this again, then those equivalent ways of defining something, one benefit is that sometimes one of those forms is much easier than the others in proving something. Okay, sometimes one form is like extremely difficult to use to prove something, and one equivalent form is like sort of you do it like this, very easy. Okay, so first order of business is establish equivalence. Establish that actually, I wrote like very weird things on the previous slide, that you need that the limit m tends to infinity of the probability of intersection n greater than or equal to m, xn minus x less than epsilon, right? That we wanted basically this to be equal to 1. And if you use continuity of probability, this is probability that union m belongs to natural numbers n greater than or equal to m. Okay, and then now out of the blue I'm writing that, we can actually write almost sure convergence using this definition here. Okay, so what is the story? They are equivalent. Okay, so that's the good news. They are equivalent, and the proofs are not basically complicated. Okay, so suppose that this statement is true. So suppose that actually the probability of this limit is, someone told you that this, the probability that limit n tends to infinity of x of n is equal to x, that is equal to 1. This is 1. Okay, so it is 1. So what is basically this limit? Okay, so what is the definition of a limit? So now forget about probability and write down this event like as if it's deterministic convergence. What does it mean? What does it mean that limit n goes to infinity xn is equal to x? It's nice to basically write it using the notation that we use for for probability. So this thing, limit n tends to infinity xn is equal to x, is review like when you studied like limits, perhaps even like in high school. What is the definition of the limit? Okay, for every epsilon greater than 0, for every epsilon greater than 0, there exists some natural number. m, such that for every small n greater than or equal to m, what do we have? We have the distance is less than right? Forget about probability. Deterministic. This is exactly this statement is this. For every epsilon greater than 0, there exists some natural number m, okay, such that for every m greater than or equal to m, the distance is less than epsilon. Okay, so there is like sort of an intersection over epsilon. And so basically, if you remove that intersection and fix the value of epsilon, then you have here, so this probability is less than or equal to this. And by continuity of probability, you can write down this probability as limit m goes to infinity with this. And now, if this statement is true, then this limit here is lower bounded by 1. And so this limit is 1. And that's the definition I started with for almost sure convergence. Okay, so if this statement is true, then our previous definition is true. The converse is also true. Okay, so let's do it. So this is one of the definitions on the previous page. Okay, so we want to show that if this holds, then this probability here is equal to 1. In this case, it is better like to work with the complement. Okay, so the probability that the limit it's 1 minus the probability that there is no convergence. Okay, so here we are saying that the limit of x n as n goes to infinity is x. Here we are thinking, okay, no, we are saying no, it's not true. So not true. Again, how can we say not true? Not true. Again, let's write it basically. So limit n goes to infinity x n not equal to x. Let's write it. What does it mean that a sequence is not converging to a particular limit? It means that there exists some epsilon. Okay, so there exists some epsilon such that for every m that is a natural number, there exists an n that is greater than or m. And what happens at this m? The distance between xn and x exceeds epsilon. This is the meaning of non-convergence. There exists some epsilon. I mean, because convergence, it's basically the complement event. So convergence means that it challenged me with any positive epsilon, and I can find an m such that for every n greater than or equal to that m, basically the distance between these two guys will be within epsilon. No convergence means that there exists at least one positive epsilon such that for every m, no matter what you do, for every m, there will be an n such that you have violation of the xn's getting close to x. Basically here, the distance between x and x will it will basically exceed epsilon, right? And try to convince yourself that basically this is equivalent to writing down this thing. Okay, so what I'm doing here, let's see. I am basically replacing epsilon by a union over a natural number. Do you agree? I mean, so basically I'm saying that there exists a natural number. So here there exists an epsilon. No matter how small, right? It can be a very, very small positive number. So here I'm saying, well, I'll just take for every there exists a k such that this distance exceeds 1 over k. They are equivalent, right? Why they are equivalent? Because 1 over k can be made arbitrarily small. So the idea of the definition is that there will be a positive epsilon, such that you can never, there will always be a violation. Basically this distance will always exceed that epsilon. Well, for any positive real number, okay, right? So if you look at the real axis, so this is 0. This is 0, right? Epsilon is a positive number. It's living somewhere here, right? You can always find the natural number that is like there, living there, right? There is always a natural number such that 1 over k is less than epsilon. Okay, so it's the same thing. So this is basically equivalent. So I mean, the idea of writing the union with an index that is a natural number, so that we apply the union bound and we have a summation, a conventional sum with the index being a natural number. Okay, so we don't want like a sum over over epsilon, which is like basically belongs to the set of real numbers. Okay, so but as a meaning, the meaning is exactly the same. Here, of course, the union bound, because of the minus sign, it is, we have greater than or equal to. So basically, the probability of this union is greater than or equal to 1 minus the sum, and then continuity of probability. What else? And then, now suppose that basically this is true. So if this is true, if this is true, so this is one of the definitions on the previous page, then this limit is always 0. What happens if you sum 0 plus 0 plus 0 plus 0 plus 0 plus, it's always 0. So 1 minus 0 will give you 1. And so this guy is equal to 1. So both definitions are equivalent. Okay, any questions? Okay, so like the alternative definition, again, which is like alternative to us, but like in some references, actually it is considered to be the main definition of almost true convergence. We can show this result. So this is like a generalization of the result that you studied in the tutorial session, right? So so if you have almost true convergence, like xn converges almost surely to x, then it must be the case that if you sum the x's and divide by their number, this will also converge almost surely to x, right? So in the tutorial session, like for deterministic sequence, right? If n converges to a, then 1 over n summation k from 1 to n, a k will converge to it, right? So the story here is the same, and so what you can do is this. Forget that those guys are random variables or anything. Okay, so Cesaro lemma basically tells you, basically this is what you start. So if you think of those guys as deterministic, right? Then if this is true, this is true. What is the proof? The proof is what we studied in the tutorial session. Okay, so we have again an event implying another event. Okay, so basically this event is at limit n goes to infinity, xn is equal to x. Then here we have that the limit n goes to infinity, 1 over n, the summation will also go to is equal to x. Okay. Now, so this implies that this event implies that event. Then the probability of this guy, is greater than or equal to the probability of this guy. So if our given piece of information is that xn, the sequence of random variables xn, converges almost surely to x, then this lower bound, this probability is 1 by definition, because we are saying that given that xn converges almost surely to x, then this probability here is lower bounded by 1, but probability is always less than or equal to 1. Then this must be equal to 1, and so what we have is that, so the conclusion is that also, if this is true, then it must be the case that 1 over n summation k from 1 to n xk converges almost surely to the exact same limit that is here. Okay, so almost sure convergence inherit many of the properties of conventional deterministic convergence. So you know that if you have a sequence an converging to a, bn converging to b, then the sum of the two sequences converge to a plus b, right? So the limit of an plus bn is, so long as basically the limits are like finite, and we don't have like problems like one limit is infinity and the other is minus infinity or something like this. Okay, so same story here. Okay, so let's see. Again, the idea here is to start from the deterministic statement. Okay, so deterministically, if this is true, that is true, and here we are thinking of those as real numbers, finite real numbers. Basically this intersection implies that the limit of the sum is equal to the sum of limits. Limit of the sum. So this, again, those are the so-called the limit arithmetics So these are the properties that make our life easy when we compute like limits, you know. So if you have a sum of functions, you can just focus on each one of them, compute the limit of each term, and then you can just sum. Okay, if this is the way to go. So we have this, and again, this implies that. This implies that. So this probability is greater than or equal to this probability, right? Again, event, you know, it's like this. If A is contained in B, then probability of A is less than or equal to the probability of B. Okay. And then this is, you know, this is something like the union bound, you know. So perhaps like you've seen this before. Like, so the union bound tells you something. So if you have two events, A complement, union B complement. Okay, so the union bound tells you that this is less than or equal to probability A complement plus probability B complement, right? And so multiply both sides by minus. So probability of A complement union B complement is greater than or equal to minus probability of A complement minus probability of B complement. Okay. Now add 1. Okay. So here 1 minus probability is 1. Okay. Now what is this probability? So this is the probability of A complement union B complement all complement, right? So by De Morgan, this is the probability that if A intersection B, of A intersection B, okay, so it is greater than or equal to, and what is this thing? It's probability of A minus the probability of B complement. So what you can do is that you can add 1 and subtract 1, and so this is probability of A plus the probability of B minus 1. Okay, so the probability of the intersection, so it is the union bound. Okay, but written in some useful way that, like, you know, if you need like a lower bound on the intersection, sometimes this is like the way to go. So again, we can lower bound the intersection by like the probability of A, the probability of B, or the minimum of the two, or if we have an infinity of them, we can lower bound by the infimum. But also in some cases, basically lower bounding the intersection by this will be the best way to go, which is probability of A intersection B is lower bounded by probability of A plus probability of E minus 1. Okay, so so this is the lower bound. Now, it's given that, you know, basically xn converges almost surely to x. So this probability is 1. It's given that basically yn converges almost surely to y. So this probability is also 1. 1 plus 1 minus 1 is 1. And so basically the probability of this is 1. And so basically we have the sum. So basically xn plus yn converges almost surely to x plus y. Okay, any question? Okay, so I will just, you know, perhaps here mention the theorem because there is no time like to go quickly through the derivation, but this will be like a strong law of large numbers. It is for independent random variables that are not necessarily identically distributed. Okay, but the proof is like sort of, it makes use of the of one of the inequalities that you have studied in the tutorial session. Okay, so so like its proof is straightforward, and then the strong law of large numbers, you know, for IID case, which is like sort of what comes to your mind when you hear the term strong law of large numbers, you know, its proof, as we will do it later, will rely on this Kolmogorov strong law of large numbers. Okay, so here we have zero mean, independent random variables. Each one may have its own variance, so they are not identically distributed. Each one may have its different variance, and we are interested in this summation here. And then there is a condition. Okay, so there is a condition here for the variance that basically if you sum the variance of random variable xi divided by I squared, and I is a natural number, then this must be finite, a finite number. If this is true, then 1 over k sk. Note that 1 over k sk is this summation of xik 1 over k. So it's basically the average, right? It's basically the sum of the x1 up to xk divided by k. It will converge almost surely to the mean value of those guys, which is all of them are zero mean, and it will converge to 0.